Good afternoon, Professor.
Good afternoon. Good afternoon, Catherine. Good afternoon, Liani. That's awesome. You beat me to it. And I'm sorry. Good afternoon, Noelia. And good afternoon and hello and good afternoon, Lolly and Michelle. Oh, wait, there's more people. I'm going to stop. Hold on. Sorry. I'm going to start again. But totally, yes. Good afternoon. And good afternoon and okay, I'm going to start. Good afternoon. Oh, no, I'm not. It's crazy time. More. Okay, let's start again. Right. Good afternoon, Catherine. Good afternoon, Noelia. Good afternoon, Liani. Hello and good afternoon, Zitlali. Good afternoon, Michelle. Good afternoon, Tomika. Oh, I like the. Oh, yeah. Right. Good afternoon, Renice. Good afternoon, capital letters Jacob. Good afternoon, Avery Yeller. Good afternoon, Antonio. Good afternoon, Janine. Good afternoon, Kirsty. Oh, wait, another person. Wait, I cut off Kirsty. Good afternoon, Kirsty, and another person's going. I just did it again. Good afternoon, Shankia. Good afternoon, Jean-Pierre. Good afternoon, Juanita. Oh, weird. And good afternoon. Wait, there's someone else coming. All right, hold on. Who did I miss? Oh, yeah. Okay. And you know what? Kirsty and Shakia and Janine and Renice just reminded me, I'm totally going to make a portal. I always think I'm going to start a different way. And Jean-Pierre reminded me, and Juanita reminded me, I'm totally going to put a portal in for anybody who has a picture or any kind of picture up. A portal of points, since you guys do seem to be understanding and embracing the whole like game portal points thing. Like I see that people are using them, which I really appreciate. I mean, most people are doing the every turn, every night, which is good. And let me repeat to all of you, like it is optional. If you've got nothing at all to write down for the day, you totally don't have to do it. It's just points there for the taking. But saying hello does count, number one. I mean, you can write number two, just to be clear, because a couple people are asking me about this. It doesn't have to be voice. Like it can, anything you do in the chat, private or public, totally counts, including saying hello. Also including saying goodbye or saying I'm leaving early or something. I often feel bad because by the time someone says goodbye or like I have to leave early, I have to go to the doctor, like I want to write back to them like it's understood or say, but they're already gone. But all that stuff counts is what I'm saying. Totally counts. Um, um, but I'm going to put a separate, but I also notice that people are understanding the separate portals, like the special portals for special extra things. Like people have already started to put things in the for right or wrong portal, which I appreciate. Like anytime anybody's had the guts to actually say a physics thing, they've put it in there. That's great. That's 75 points. Some people have already put stuff in the portal for closing a conversation, which was totally new, just went up. I appreciate that. I did notice that at least one person actually did subscribe to the YouTube channel, which does make me happy. I feel sheepish saying it, but they should submit that into the YouTube or the you subscribe portal, whatever, and get points for that. I'm going to say now, it just occurred to me that anybody who's putting a picture up of any kind, a picture up, in the Zoom, it really helps. And like, if nothing else, it makes our screens like less, um, dead. So it doesn't have to be a picture of you. It could be a picture of just like anything that I can just then associate with you. And then when I finally meet some of you in 15 years in a research lab somewhere or something, or working for the government or whatever, I'll be like, oh, you're the rabbit icon, and at least that's something, or the rabbit avatar. So total point, I will put a portal in for that. And it doesn't, yeah. Wait, private chat. Well, look, to make sure there's a private chat. Any icon counts as a picture. Let me see what icon. Oh, yeah, I guess because right. I mean, well, I don't want to give away who just asked that, but sure, right. I mean, oh, it's funny. Why is that true for some of you and not others? But yeah, I mean, if you're really pressing me, I guess I realize that some of these icons maybe take more effort than that, but yes, as long as it's anything at all that you made the choice to put in, that's not just a black box that just automatically says your name in white. And again, that's not to criticize the people that haven't done this, but if you take 2 minutes to just like color your square slightly different, just so it's easier for me to find and see, I say that's points. So I'll make a portal for it. Yes, any of these, including the letter icons. Oh, cool. Oh, and for that private chat person, just close the conversation in a way that totally gets points. But okay, not going to over. Also, sorry, I've been sick for the last 3 days, so I'm doing all kinds of gross things while I talk. So, and good afternoon, Hoyin. Thank you for saying so. Good afternoon. That totally counts for points. Thank you for saying so. And good afternoon, Shamari. Great to see you both. Thank you for saying so. That is a smart thing to do. And if I'm like sneezing and snotting through this whole class, I totally apologize. But in this political climate, if anybody's sick, they should always pick a politician that they don't like and blame it on him, right? I mean, whether it's Fauci or Trump, just blame it on them. It's their fault that I'm sick, I'm sure, somehow. And I'm kidding, by the way. I'm kidding on both of them. Okay, so I think we can start. So I think we can get more rolling today. What do I want to say? So now a bunch of you, so, okay, my usual speech. Oh, thank you for the LOL. Oh, that counts too. Well, that counts for something. If I get an LOL, that's got to be points somehow. Excuse me. Wait, I'm going to take 1 second to check on one thing about the homework I wanted to say. Pardon me for a second. I always accidentally check these things on my tablet and then it goes up on your shared screen, which is not what I mean to do. So hang on a second. I just want to check. Homework 3, right? Okay, yeah, homework 3, which was technically due today. We may or may not get up. Well, we're going to say a lot of things today that I'm going to try to cross-reference to homework 3. We're going to say a lot of things today that I think you'll see how they relate to homework 3. And I'll try to remember to literally point that out when that happens. More formally, we're going to be dealing with homework 2 finally today. Hopefully some of it will fly through a little bit quickly, some of it. But what I want to say is now, technically 3 was due today. 10 of you have submitted it. I congratulate you. I think that's awesome. I think that means you had to try something that might have been a little bit of a stretch. You might have been able to pull some things from lab in there. You might have been able to pull, like, technically where we got yesterday, by the end of yesterday, technically, everybody in this room now has enough information to technically to do not only all of homework 2, well, yeah, to do homework 2, but also to do homework 3. Like technically you could do homework 3 from the information that we got by the end of yesterday. And technically, since it's homework, you could say that it's like practicing that information. But we both know, to be clear though, that in order to do anything, even practice, we need practice. So today we're going to be doing like practicing the stuff that we got to at the end of yesterday. And that might make homework 3 a lot easier for a lot of you to approach. Like it could look very hard right at first. Homework 3, that is. It's short, but it can look impossible right at first. But once you see what it is that we established yesterday, and once you see what you've established in lab, you'll find that it's a lot easier. I shouldn't say that. It's a lot, I think, a lot less stressful than homework 2 was. So I'm saying congratulations to anybody who got homework 3 in today, and totally if they want to like screen, that counts as getting things in super on time and you can get extra points for that. I'm acknowledging, I'm not sure if I want to say your names or not, but I totally got it from you. I'm, technically it was due right now, so I have not turned it back around yet. But anybody who has not done homework 3 is still plenty of time to do it. I know I keep saying that. I just want to reinforce this. I've now turned back all the homework 2s. So I see where you're all at with calculus. It actually was really hopefully instructive to you, but it was also instructive to me to kind of see where people are at with their background in calculus. All of you have gotten, anybody who's done homework 2, I hope has gotten it back by now. Anybody who did not get full score can still get a full score. I know I keep saying that, but I am getting questions about it. And maybe it is kind of hard to believe, or, we're just habituated to being stressed. Let me just reinforce the whole method of grading in this class is just think of it as there's a there's just a pile of points out there that you're just trying to pile up. And the bigger your pile is by the end, the stronger chance you're going to get an A. And there's no limit to, and if everybody makes a big enough pile, then everybody gets an A. And if you don't make if you don't make a big enough pile by the end, and your exam scores aren't sufficiently high, then you don't get an A. And that will happen to some people. But you have till the end of the course, basically, or until I seriously make some serious announcement that the hammer has come down on something like homework 1 or something, unless I make an explicit serious announcement, like I'm no longer taking homework 1s or something like that, you have till the end of the semester to accumulate all these points. And that can mean by returning in and returning in and returning in anything until it's perfect. Okay, everything is a draft as far as I'm concerned. So anytime you don't get full, I know I've said this before and I'll move on in a minute, but I just want to emphasize again, if you ever get a score that is less than the full score, that's not me punishing you. That's not me saying you are an insufficient person or something like that. That's just saying there's still a gap that you could still fill later. And it could mean why don't you just wait till we go over this in class, and then you'll really get it, and then you can turn around and hand in another document. It's not cheating. It's the way this class works, for good or for bad. Okay, so so the points are like signposts along the way of how much more work or how much work you have done like successfully and how much more work there is to go. And you just keep going in sequence like that. Okay. But I think people are, I actually do think people are understanding that. And I'm very pleased with all a lot of the homework twos. It was clear that many of you weren't totally comfortable in certain parts, but you sort of like worked your way through anyway. And that's the idea. Oh, just one last thing, the one thing, please. I think people are getting really good, and I appreciate this. People are definitely taking me seriously on the issue of how to start a problem. Like you're putting the question down in your own words, you're putting the givens down in your own way, which I need. You're setting it up so that I can follow your question without looking at a separate problem sheet next to me. Like, and that is the idea. And I totally appreciate that. So then just to follow that through and bring it to a beautiful close, then please, when you get to your final answer, circle it or highlight it or something. Like just make a trombone sound a big emphasis where you get to the final landing place. It shows that you have closed the conversation, that you know what the conversation was all about, that you know what your goal, you achieved it. And it also makes it a heck of a lot easier for me to go through the papers efficiently. Wait, someone's in. Put another way, if you were writing a research article, it makes it a lot easier on the reader to know when you're at the intro and when you've arrived at what you think is your conclusion. And so please do that. And if I say PCF, is that no? If I say PCA, which I don't do a lot, but if I say PCA and like I circle the C or something, I'm just saying please circle answers. Okay. Oh, and totally good afternoon, direct message person. I won't say your name, but yes, good. And yeah. Wait here. Okay. First of all, good afternoon to person in direct chat. Thank you for saying so. I appreciate it. And you can totally screenshot that. Okay. But also another direct chat or direct message question. Yeah. Okay. And this is why, again, I'm glad people are asking me this. Yes. Even if this is so important. And again, I apologize to anybody if you think you've heard me say this before. Maybe I have. It's okay. It's super important. Even once I've gone over answers, you can still upload them. Yes. And the reason it's worth me saying that more than once, the reason I'm glad someone has the guts to ask that at this stage, is because I know that's unusual. That is unusual. That is a surprise. It's not obvious at all. It's just that it's true. So let me say it again. You can still, if a homework was worth 350 points, and you only got 280 points or something because you left the middle section blank because you had no idea or whatever, or you left some, and generally, again, if you lost a lot of points, it generally would be either for a formatting thing or that you left something blank. Generally, if you fill out everything, you're going to get really a lot more points than you might think. But anyway, if you left a big section blank because you just scared you, or you just never seen that thing before, or blah, 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 and you're an honest person, you didn't just want to cheat your way through it. If you left it blank, so then you didn't get all the points. If I then go over it in class, which is totally what's going to happen today, you still can then turn around, do your homework, you finish your homework, return it in. Please do return in a complete document, like submit the whole homework with all the parts, even if I've already graded some parts. And if you think there's any ambiguity, write me a note, like in the homework, say, this is the deal. Like, this is my second version of this homework. The first version didn't include section 2 or whatever, but submit it to me. Even if I've already gone over the answers in class, you totally still can and should do that. I'm saying that to everybody. Like, you're trying to show me by the end of this course that you know all of this stuff, and you're trying to get like all the points you can for all the stuff I'm asking. And it's ideal to try these things before I go over them. There's countless benefits and rewards that come to a person who tries this stuff before I go over it. And some of those rewards are in straight up points, and some of them are not. They just like come out. You can't count them, but that person will feel will know the stuff much better by the end, blah, blah, blah. There's lots of rewards and benefits that come from trying this homework before I go over it. But there are also countless rewards and benefits from doing it and showing that you get it once I've gone over it. Like, once you've done your job of attending class and gotten something for your tuition dollars. Like, okay, so that's why the class is designed. You can do yes, I don't mean to be yelling at anybody, but I know this is unusual, or it's like seems weird. But you can still get all your points for the homework, even if you turn it in even after I've gone over it. Now, there's two things to say about that, though, because I know that might strike some of you as weird. First of all, I know it might seem unfair, like to the people that killed themselves before I went, the people that kill themselves with homework before I go over it and try their best and look things up and remember their calculus or whatever, and they do all this and take the risk of making mistakes, and then I see their mistakes, blah, blah. They do all that. They might be saying, well, that's unfair. Why are these other people just like sitting around, not doing anything, and then waiting until after like he goes over the homework and then they're posting it in and then they're getting full credit? What's that about? My point is, first of all, I know the difference. I know that some people are handing in the homework before, and I'm seeing what you're doing before I even go over it. Believe me. And that's why I'm trying to get it back to you and communicate that. Believe me, we're having a communication event about this material and advancing both of our understanding before the other person even steps into the ring, right? You're getting points and credit and like affirmation before they step in the ring. I'm getting to see what you know, blah, blah, blah. Second of all, if a person deliberately never does their homework at all, doesn't even try, and just keeps waiting for me to go over it and then tries to turn it in, believe me, they're going to fall behind so fast, and they're going to be stressed, and they're not actually going to be understanding what's going on the way the first person is. It's going to catch up to them, and the first person's A is not threatened at all, no matter what the second person's grade is going to be. Like, the only reason the first person should feel threatened by that second person is if they thought I had a limited number of A's to give out, and that I could be fooled by the second person into giving them the only A. That's not going to happen. But the other thing I want to say, is every conversation's better if each person's thinking about it in advance. The second person, I'm saying, I'm overdoing this, but I'm saying everybody learns in a different way. Everybody benefits from thinking about things before I talk about them, and that actually gives them a reason to listen to me. But people also benefit, hopefully, from me talking a bit in class. Otherwise, like, why are you spending all this money and time on Zoom with me? So it's all about us all trying to get it whatever way we can at whatever pace we can. So everybody gets credit for the homework once they've done the homework and however they do the homework. And last thing that's the most important. Let me also tell you, all of this is training. All of this is designed to be training for the exams, and especially the way the exams now work in COVID. It's all meant to be training for the exams in this class and maybe later life, at least in some areas of at least physics research. What I mean by that is this. By the time you get to the exams, and I know some people in the room already know this, some people don't. By the time you get to the exam is going to be a take-home document that's untimed. It's just going to be a massive, massive homework kind of experience in a way. It's more almost like an essay of problem solving kind of format than it is an exam format. So by the time you get to the exam, you're going to be going home and having infinite resources. Google, your friends, your uncle, your aunt. You're going to have whatever resources, whatever time you want in order to solve the problems that I give you. And some of those problems I would have already given you solutions to on a practice exam, honestly. Like I will literally give you guys problems where I know in advance that you know in advance the answers. But your job on the, and so that will level the playing field, and no one will have some like tricky advantage over anybody else where they actually have access to the secret Wikipedia article that no one else has or something. Everybody's going to have infinite resources. The goal of the exam is to show on your document, show me that you actually understand why all this physics is true, why this physics works, why the answers do follow from basic principles. That's your job on the exam, is to do proofs, to prove the physics and prove that you actually understand your proofs. That's what we're training for on these homeworks, or like trying to practice. You're using these homes, so it doesn't matter. I know I sound like I'm yelling, but it's such a good question. And it was a question in the private chat anyway. But the question again was like, can we still like turn in the homework and get full points, even if it's after I've gone over it? The answer is yes. Yes, yes. I don't think it's good practice for you just to then make a habit of sitting around and waiting for that. Like, don't just rely on that. I think that would be a mistake and you would suffer. But it's not too late to turn in your stuff after you've heard my stuff. Because what you're doing when you turn in your stuff is you're showing that you've now learned it. And that's what you want to do in homework. That's why I keep talking about these formatting things of like, start with the question, then do algebraic then do fundamental definitions or fundamental laws, then do algebraic manipulations, then plug in numbers, then watch units, then circle your answer and talk it through while you're doing it. Like give me as much explanation as you can. You're there in the homework not to show me the right answer. I already know the right answer. Hopefully you're there to show me that you actually understand why the right answer wasn't just a question of memorization, but actually followed logically from first principles. That's what and that can be done at any time. If I can, that's what I'm trying to do for you in class, is show you that this crap actually makes sense, that it's not just like a bunch of fragmented knowledge. And then you show me back on the homework on the exams that it actually makes sense to you. And that can be done at any time until the course is over. Like that's my big speech. I'm sorry, I'm doing it again, I know. But yeah, anytime. The thing about deadlines and scheduling is this just to show you the sequence of stuff and to show you what comes first, what comes second, and to help you, because we all know that once we start falling behind, it becomes harder and harder to do stuff. But I almost never will actually penalize anybody for like being late, unless it's an exam. Like exams are more important. We'll get to that. Like exams, you can't turn in late. I mean, there's reasons for that. That gets into fairness and stuff. But just keep trucking along doing what you're doing. I'm going to shut up. I'm going to look at the, yes. Oh, okay. Sorry. Okay, there's more in the chat. Oh God, I'm sorry. Okay, yeah. Wait, are we recording? Yes. Okay, we're gonna get to. We're gonna say, but before. Okay, wait. What did I want to say? But everything you guys have turned in so far really show. I really think we are having communication. Honestly, I do. Like I've seen a massive improvement from homework 1 to homework 2. Massive improvement, and I think homework 2 is way harder. Like homework 2 starts with questions that a lot of you have not thought about for 2 years and never liked when you were thinking about them. Homework 1 at least looked like normal physics at first, but there nonetheless was a massive improvement from 1 to 2, because I think you actually are hearing what it is that I'm asking you to try to do. So and again, if you still haven't handed in homework 2, you still can. So I think everybody's doing fine. And and I just get afraid of getting in the soup, talking about this too much, but the exam. All right. So I'm seeing, so yes, good afternoon. How many questions now, if Jacob's question, I believe, is about the exam, totally fair. And I really do want to answer all questions about the exam when we get there. And I guess we are getting sort of close, but I don't want to spend today. But the bottom line answer is probably 3, maybe 4. But the exam is probably 3 problems, like problems. So a problem I could say, like homework 1 is the model. That's why we spent so much time on it also. Homework 1 is one big problem, right? It had like 9 parts, but it was one big setup, one situation, and then a progression of step-by-step questions about the situation that ultimately landed on sort of a punchline, on sort of like all the questions are meant to build up to the last one. That I consider to be a sort of classic physics problem. And you'll probably have like 3 of those on your exam, which you will know in advance what they are. I'm just not getting into it today, but you'll have a practice document before then to know what they are. But yeah, you'll have like 3 like fact pattern and then question. And you'll be what I will say is every little thing I'm saying about homework's like, please do it this way. Please start off with the question. Please, that's totally what I'm asking you to do on the exam. It's all the homeworks are just like mini exams, in that sense, in the formatting sense. And you will get an equation sheet on the exam, and you will have open everything. There'll be no hidden resources. But yeah, so the answer is 3 problems probably, and you'll know what they are, or certainly the type of problems that they are before you get there. What's it? And how much time? How much time you'll have? And I think I think this is saying, well, yeah, okay. How much time? I was about to say, it is a little more compressed since this is a 5-week course and all that, but you'll have a couple of nights. All right, let me think this through right now. Wait a second. Yeah, I guess I do have to answer these questions right now. Oh yeah, I know, because this thing goes so fast. All right, all right, let me think this through right now, because I know that I will fully and officially confirm this on Monday, and I don't want to scare anybody or anything like that. Well, probably. And I know this is going to get into your life, but I think this is just the nature of a 5-week course. I don't think it's avoidable. Most likely, we still have more material to go today, obviously. Most likely, I will post the exam Wednesday night. Like, we'll have Monday, Tuesday, Wednesday to prepare for it. Monday, we'll keep doing material. Then Tuesday, like, I'll give you a practice exam. I mean, to show you, we won't sit in class and do it right then, but I'll give you a practice document. Maybe Wednesday, at the beginning of class, I'll give you the solutions to that practice document, something like that. So, but in other words, we'll prepare and ramp up for the exam Monday, Tuesday, Wednesday, and then Wednesday night. I'm saying this informally, and I'm saying it because you're right. We better work this out, but let me think about this in the back of my mind during class day. But probably I will post the exam Wednesday night. Like, it'll become available Wednesday night, and probably I'll say that it's due Saturday morning or something like that. So that ideally that I can grade it over the weekend and we can have it go over and put it to bed by Monday, ideally. So in other words, so the good news is it is totally take home, and you won't have, test conditions that you have to do it, and you'll have like a few nights to do it. The bad news is those nights will be, during your weekend or your off time, but I think that's the way homework and everything often goes for these 5-week courses. So probably I post it Wednesday night, then probably I make it due Saturday morning so I don't ruin your whole weekend. Possibly I do ruin your whole weekend and say you have till Sunday night to do it. I might say that. I have to think about that. I might even take a vote or something, but not right now. But it'll be posted Wednesday night, and you'll have at least 48 hours to do it. That much I can say. It'll be posted Wednesday night. You'll have at least 48 hours to do it. I can stand firm on that. Let me think more about the details as we progress today. But again, to everybody, it's a take-home thing. It's just, and you'll submit it to Google Classroom. It's just like these homeworks. It'll feel like these homeworks, only bigger and count more, and and correct answers will matter. But okay. All right. And this is the other thing. Oh, great. Perfectly put. All right. So I just got 2 things in the I do want to move on, and I do want to deal with material because we have to for the exam. But these are fair questions. And since I just spouted out a partial answer, I just got 2 things in the direct chat that asked me, please, to consider something. Super polite things in the direct chat that literally said, could you please consider? I'll tell you what they asked me to consider in a minute. That is perfect phrasing. I'm all for that. While I'm teaching today, so as long as we agree that I have to press on with the material now, and I don't want to have an open discussion about this for too much longer now, I have no problem if any and all of you, if you start putting opinions in the direct chat, that I won't stop on a dime for them, but I'll read them. If someone just put in the someone said, Professor Walters gave us the whole weekend. Is it possible if it's possible, will I please consider? Absolutely, I will consider that, especially because that's such a reasonable, you can see I'm on the fence anyway. That's such a reasonable way to put it. Any one of you who wants to put in a suggestion or request, as long as you put it politely like that, and as long as you understand that I might have to say no, depending on, you feel free this class to put suggestions or requests like that in the chat. And I'm not going to deal with them all at once, but I'll read them all and take them seriously. So right now, my instinct is I'm posting the exam Wednesday. I was going to say like turning around Saturday because I'm worried about time efficiency, but I'm totally now considering giving you the whole weekend to do it and saying it's due Monday. I don't have a principled problem with that. But hopefully I'm giving you a clear enough picture right now, a clear enough draft picture of what this looks like that, yes, I'm going to start class, but you can, or it doesn't have to be the direct chat. It can be the public chat, so you can influence each other. That's up to you. But just as long as we both agree, if there's questions or issues about the exam, then right now I won't like stop in an instant for them. I'll like consider them toward the end or something. So put them in, do please, but just forgive me that I'm going to start going over material. Oh, that, yeah. Okay. So I'll okay. I'm going to start in a second. I'm just going to, well, all right. No, there's one more question I guess I should answer. All right. Another fair question in the direct chat. Well, let me think about that. There's another thing I'm going to think for a second, but I want to go on. Hold on a second. Okay. All right. So I'm going to get, so again, I am taking everything in the chat. I did just respond to things in the private chat. I'm taking them all seriously. I promise. Hello. All right. All right. I see it. That's awesome. That's awesome, Catherine. So yes, I'm taking the things in the private chat seriously. Once I get rolling now, I will probably ignore them like for minutes if they're about the exam, but I am taking them seriously. I probably will already backpedal and give you the whole weekend. Like I just have to, I'm just concerned about time. That's all. But oh, okay. Thank you. So I just like let it churn in my brain. Okay, but I do want to get to the material because that's, oh, and the last thing for good or, well, I probably shouldn't say this now, but you know, I think what's maybe is understood by everybody, what you get examined on is whatever we do in the class, period. You don't get examined on anything that's like sitting in a textbook somewhere that we didn't get to or something. You literally directly get examined on whatever we do in class, which again is also why if you miss class, you should watch the YouTube videos or whatever, because that, or at least take the PDF of the notes, because that's what the exam material is. But that, and that's it. So it's like all about class. but that's also why I think I better use this class time to press on. So, okay. So I'm going to summarize what we got yesterday, hopefully quickly. And then we're going to directly go to homework 2 and maybe 3. Well, yeah. Okay. Actually, this is one way to write it. I'm gonna make a correction here. If you hold on a second, just what I just wrote is correct. If you want to keep it, it's fine, but it also might be confusing to some people, so I'm going to write it this. Okay. I'm going to do another page in a sec before. Okay. What I'm saying is, and this is supposed to be a T here. This course all started with a mass on a spring. And it had numbers associated with it. The spring had a stiffness of 200 newtons per meter. The mass was stretched to an initial displacement of 15 centimeters. The mass was 0.3 kilograms. And after like thinking about the mass for a while, we ultimately said, all right, after 1 second elapses, where will we find the mass? So it starts off by being a very particular numerical question. Given this mass of these properties, like where will it be in a certain amount of time? We did a bunch of work, a bunch of math work. And in order to step back and say, all right, actually, can we even understand how to make this prediction regardless of the numbers? Like just given any kind of mass on any kind of spring, can we name the position if you name the time? In other words, we started looking for x as a function of t, and we found that that if this let me catch my breath. Okay, we found that the physical law of Hooke's law, the physical statement of Hooke's law for any mass on any spring can be written mathematically. And once it's written mathematically, it's a differential equation. We solve that differential equation in order to get x as a function of t. We got, oh, good question. Yes, I will be posting homework for today. Thank you for reminding me. Yes, I will. Thank you for reminding me. I didn't yet. I will. And also game turn 5. Good point. Thank you. Sorry, I'm totally distracted, but not by that. Okay, we found that the physical statement of Hooke's law is a differential equation mathematically. So we had to solve it mathematically. We solved it and we got a cosine function, x equals x naught cosine omega t. We found that that cosine function totally makes sense and can totally work and can totally allow us to make the prediction we're looking for. Like we were able to apply it to the numbers we were given. We finally got something where we could just plug in numbers, which is sort of like what people are often looking for. We got something that allowed us to just plug in numbers as long as we understood how all the constants were related, right? Like I get what I'm trying to say is we solved the differential equation kind of in general terms, but part of our job in solving that differential equation was being able to relate the constants to one another and find out what the constants meant, that making them, in other words, not just arbitrary, solving for them like we did in the sidebar problems 2 days ago. So we found that x equals x naught cosine omega t is a statement that we could take to the bank and use to predict the motion of a mass on a spring, as long as by omega, as long as by this rate, this angular frequency, we actually mean something that relates back to the physical parameters of the system. Omega, we found, equals the square root of k over m. Like our solution works as long as omega squared is just another name for k over m. Therefore, in the end, we not only got a mathematical solution to our mathematical problem, but we also got some knowledge about constants. We got some knowledge about when we say in the end, and this we were going to start applying to the homeworks, when we say in the end omega equals square root of k over m, in this case, k is a spring stiffness, m is a mass. That's sort of interesting, but even that is sort of just particular and specific to the situation at hand. The real important thing is that omega had only to do with material properties of the system. It had nothing to do with the way the system was set up. What this says in step 3 is that omega is not a function. That's what I mean by that f there, right? Like I keep using that lowercase f to mean function of. Omega is not a function of x naught. Not just that it's not a function of t or x, but it's also not a function of x naught. The rate, what that means in English is the rate at which this thing goes back and forth is totally determined by how strong the spring is and how massive the mass is. It has nothing to do with how far out you initially place the mass. That is actually kind of interesting. Actually, it's very interesting. What we're saying is that this thing will oscillate at a rate in time that has nothing to do with how we configured it in space. What we're saying, put another way, is that the amount of time it takes to do each cycle doesn't depend on how large the cycle is. That's kind of a new breakthrough. I mean, you're going to see that more and more, but that's kind of weird. That is what we mean by harmonic. Like, and I'm about to look into direct chat. I see something in direct chat, totally cool. So hang on a second. Anything that goes back and forth is oscillation. My hand is going back and forth right now, and it's going like it's oscillating. It's doing it in like a very haphazard, like unsteady fashion, but it is oscillation. If it starts going in a steady fashion, we might start to consider calling it harmonic. Harmonic means steady, but steady in a very super specific way. This is how steady harmonic means. It means not only is the rate at which something's going back and forth a constant, like a number, like it's doing 3 vibrations every second or 3 cycles every second or 36 radians every second, however you want to say it. We're saying not only is that a constant number, but that constant number would be the same whether we were going like this or going like this. Like whether we start the mass on the spring at 15 centimeters or 37 centimeters, we're saying large swings or small swings will take the same amount of time as each other. That the amount of time is totally determined by what the spring is made of. That's what harmonic means. That's what we're talking about here. And the harmonic solution is x equals x naught cosine omega t. I'm going to pause. So that's a big, so what we've done so far is, at least for a mass on a spring, we've set up the math that describes it. We've solved the math that describes it. And then we've discovered something from that math that if this thing is oscillating the way it looks like it is, the math shows that it's actually apparently oscillating at a rate that we can predict and determine before the thing even starts moving. And we can predict and determine before we even decide where to move it from. Like that is something that I would have never known in any question 1 through 9 in the first homework. Like that is not obvious just because something's on a spring. It turns out to be true because we just derived ultimately an omega as that was the square root of k over m, and nowhere in there is an x naught. Omega is not dependent on x naught. That's like our final discovery and why it was sort of worth going through solving the differential equation to get this. And that so we could predict the motion too. I obviously have more to say, but hold on. There's a good question in direct chat, I think. Yes. Sorry. Great question, direct chat person. And please, 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 direct chat person, please screenshot that and put that like for your homework thing, because I know who you are and I know that totally counts as participation. And there's no reason that needed to have been private. It's a great question, but yes. So the question was, are these 3 things all under simple harmonic oscillation? Yes. I'm actually trying to argue that these 3 are almost equivalent state. These are the 3 legs of the stool that is what we mean by harmonic, that type of special oscillation. Harmonic is defined by that differential equation, but that differential equation has the solution that we've now verified, and it follows from that solution that the constants are related in the way that they are. So we can ultimately say in English about harmonic oscillation in English. So tell me if you want me to go. But so yes, okay, cool. Oh, she or he can now double dip. They can totally double dip that conversation both in a, actually they could triple dip it, because the thing that was in the direct chat was like something that could have been right or wrong. Like I could have said yes or no. So she or he could put it there in the right or wrong. They could put it in the like the everyday regular turn thing, although I forgot to post it for today, but I will. And they could even put it in the circle back, like close the conversation now thing, because that person said got it, thanks. Okay, which I've now like wasted everybody's time by talking about, but okay, so that's awesome. So what I'm saying is this. Okay, I'm gonna say now, and yeah, someone may want to remind me in the thing. I do have to pause at some point in the middle to post the homework. I forgot at least the game turn. I will do that. But what I've been trying to say again is we started with something numerical and particular and real, and maybe even experimental from the lab. But then we say, it doesn't really matter what the numbers are. We just put in symbols for those numbers. Like it doesn't matter 0.3 kilograms. We could just call it M, and we work from there. And we did all this math, this kind of high level math. The thing about math is math totally doesn't care. Math is exactly the subject that doesn't care what your particular details or your particular situation is. It's just math. It's always true when it's true at all, right? So that actually and that's why some people love it and some people hate it, or why we love it sometimes when it's working for us and we hate it when it's not, because it's just there. Well, we're going to take that advantage now and go a step further and say, look, I'm saying that we had this differential equation d2x d2 squared equals negative k over mx. And I made a big point of saying, okay, k and m are just constants. Like they're just numbers. So one number over the other is just a number. Someone's here. Sorry. So I didn't really care whether we changed the name of k over m to c3 or omega squared. Well, right. So in the same way, what we could say is, hang on, if we ever face that differential equation, if we ever run into any system that is obeying that differential equation, even if there is no literal coil of spring, and even if there is no literal block of mass at the end of that coil of metal, as long as the system seems to obey this relationship, as long as the system, we have some reason for believing, has an acceleration that is directly proportional to displacement, then the system will obey all this math. So in other words, we can generalize beyond this and say, okay, that's supposed to be a lowercase z. That's the way I write z's, just so they don't look like threes, but they probably look like, anyway, that's supposed to be a lowercase z. And I'm going to use it now to mean any variable at all. Like I could use q, but it's supposed to be any dependent variable at all. Okay. I mean, could be a position variable on the x-axis, could be on the y or z axis, could stand for angular position, like in your second lab, like in the pendulum. Z could stand for, like, in other words, I could be using it the way you use theta usually, or Z could stand for some other thing like temperature, as in homework 3, or electric field, as in what we're getting to. Z could stand for anything, okay? If Okay, let me try to explain this. And always the most important thing always gets crammed at the bottom. really gotta work on that. Um, what I'm trying to say now is I'm just taking what we already proved, like what we finally derived for the case of homework 1. We figured out something about a mass on a spring, but you've already been in a couple of labs and you're seeing that somehow we're applying that reasoning already to other systems in life that don't have springs and don't have like blocks on tables in them. Like they look totally different. What we're saying is everything we figured out about the mass on a spring, we figured out mathematically. And the math doesn't know that we had a spring, or it doesn't care that we had a spring. The math doesn't even care that the math doesn't care about units. I mean, it's one big difference in science and math. The math does not care about the units. So the K was not measured in newtons per meter to the math or anything. K was just a constant number. So was M. The square root of K over M ultimately became this constant number called omega, and what was omega? We have to talk a lot more about it, but what omega was the rate, the wiggle rate of that cosine graph. Omega was, in effect, the number of radians per second, i.e. the number of up, down, like squiggles, the number of periods, if you like, the number of cycles that graph would undergo per some section of the x-axis, per time, ultimately, right? The omega is the vibration frequency measured in kind of funky units, but that's what it is. It's how rapidly the system goes back and forth, goes back and forth, goes back and forth. What I'm saying now is the math didn't care. We found that if d2x dt squared equals negative k over mx, then x equals x naught cosine omega t, as long as omega, by omega, we mean the square root of k over m. Well, what I'm now saying is, mathematically, I didn't have to put a k over m in there at all. I could run into any differential equation. I could run into any system, such as a pendulum, such as lab 2. I think it's lab 2. If I run into any situation that any independent variable that I think is that I have reason to believe is being described by this differential equation. If I have any dependent variable whose second time derivative is directly proportional to it, that's really what I'm ultimately saying. If you find any function in life, any dependent variable, anything that you're measuring, could be position, could be angular position, could be speed, could be color, as long as like you can numerically like map colors, could be temperature, could be electric field, whatever. If you find something that you're measuring and you find that that measurement obeys this differential equation, you find that the second time derivative of that measurement is directly proportional to the measurement itself with a negative sign, then necessarily that measurement is harmonically oscillating. That's what I'm trying to say right now. So like as long as this differential equation applies to pendulums, then the angular position of a pendulum harmonically oscillates. And what it means to say that it harmonically oscillates is to say that then we can know right away that a cosine function can predict the measurement for any given time. And more specifically now, here's sort of the tricky part. I'm saying that, and this is why I'm going to write. So from now on, whenever I write this differential equation, I'm not going to write it with k's over m's. I'm dropping the k and the m, just like when we put in the k's and the m in the first place, we dropped 200 and 0.3. I'm getting more and more general here because I'm trying to understand the universe, right? What was k over n was the specific material properties of a specific mass on a spring. I'm now saying I don't care what system you have, as long as you have a differential equation that adequately describes it, and as long as the differential equation can be written this way, then I'm going to call as long as the second time derivative is negative times a constant times the measurement, the independent variable, whatever that constant is, I'm going to call omega squared. Whatever it is, I'm going to call omega squared. I could have called it anything, but I'm going to call it omega squared. I'm specifically going to call it omega squared because then I know the solution will be variable equals variable naught times cosine omega t. specifically, like I'm intentionally putting a square here in the red parentheses. I'm not putting a square in the cosine argument, because what I'm specifically trying to say is, and this really, really is what homework 3 is all about. I'm really saying that whatever that constant is, the square root of it will be the rate at which the system oscillates, regardless of how you configure the system. The rate at which the system oscillates will be steady and constant and will be fully determined by just being the square root of whatever that constant term is. So I'm saying the English, the last bit of the page says, then Z will oscillate at an angular frequency of square root of that constant, like whatever the constant is. So if I call the constant omega squared, then the square root of that is omega. And that is why I usually do call it omega squared. This sounds abstract. I'll give you, we'll see more examples when we go through the homework. But one last, I'm saying, and stop me if you want me to go back. Okay, I'm going to ask you, well, I'm going to ask you to put 2 more things in your notes so that I'm just to read this out. I'm saying in English, any system which can be found to obey that differential equation. And we can find that out about systems often by taking data in the lab or whatever. Like if you have any reason to believe, and there's lots of different systems in the world that don't look, there's lots of systems in the world that don't look like they have springs. They don't look like they have pendulum strings. They don't look like oscillators. But any system in the world that can be said to follow that differential equation, if we have any independent reason to describe that system with that differential equation, then we can know right away that it's a harmonic oscillator. And that means that we know right away oscillating, sorry, someone's here. It'll be oscillating, first of all, back and forth. And sometimes you can't even tell that, like we're saying, sometimes you don't even see that in the system, but you can realize it if you know that the differential equation applies. We'll know right away that a system is going back and forth and back and forth. We'll know right away that it's going back and forth at a steady constant rate. And the big kicker of what I'm trying to say that I'll keep saying throughout the course is that as long as the system can be described by that differential equation, then we know that the steady constant rate that the system is going back and forth at is one that's fully determined by parameters, not at all by configuration. I'm going to ask you right now in a separate page of your notes to define these 2 words. I don't want to get, I don't want to turn the page just in case anybody's, but parameter, the definition of, so please write this down if you take notes at all. And also, side note, those of you who are like quieter people, which I totally understand. I mean, I can't relate obviously, but I understand. I keep forgetting to mention that for the game turn assignments where you're supposed to show like your participation in the class, you can, if you're taking good notes, if you're taking your own notes, you can totally scan a piece of notes into your computer, or like take a picture and screenshot, whatever. You can send an excerpt of the notes you're taking as an indication of a way that you're participating in class. I would welcome that. I actually love people seeing student notes. Like, really, it tells me a lot. So you don't have to talk to be part of this class, but just to show me that you're engaged and you're with me. If any of you who wants the 50 points every day, you can totally screenshot your notes. But anyway, and I do encourage all of you to be taking notes, even though I am, for 1,000 reasons. But so in your notes right now, please, I'm not going to write this for weird reasons. I'm not going to write it. I'm asking you, parameter, the triple equal sign, parameter equals material property of a system. A parameter is a material property of a system. Something like the mass or the stiffness of the spring, something that can be measured in a lab in advance of doing anything with the system at all, like something that would be stamped on the bottom of the system ingredients, like in the factory. That's what a parameter is, okay? A parameter is a material property of a system, literally like property of the materials of the system. That's what a parameter is. Configuration is a condition. Configuration is how the system is set up initially, okay? So I'll say it one more time. A parameter is a material property. A configuration is a condition. And again, anybody can stop me in the private chat or whatever if you're sort of catching this at all, but not fully. I'd rather know. Yeah, sorry. Okay, good. The word after that is okay. Oh, great. Yeah, sorry. The word after that is fully. Sorry. Great question. Sorry. I think that's what the question is. Yeah. Sorry. So yeah, I'll read this out. So I'm saying for any system which obeys the differential equation that we now have at hand, oscillation will occur at a constant rate that is fully determined. Thank you. Awesome. And that was a closed circle. Thank you for the thank you. Okay, cool. Points. Okay. Oscillation will occur at a constant rate that is fully. Yeah. Okay. All right. I'll read it one more time and then I'll look in the chat again. Yes, correct. Wait. Oh, yes. Now, Romy, and thank you for putting the public chat. Answer is yes. I mean, answer to your question, oscillation will always be constant. Correct. Yes. And so I'll just read it one more time. Oscillation will occur at a constant rate that is fully determined by parameters, not by configuration. Fully determined by material properties, not determined by conditions, like not determined by how we set up the materials. So very specific. So I'm saying this is even. Oh, no problem. Oh, I did get that wrong. Okay, I got you. No problem. My family changed their name at Ellis Island. Can you believe it was even longer than Yaverbaum before we came over? No, I'm totally kidding. That is not true. I mean, it is not true. It is true, by the way. Okay, this is so ridiculous. My name is Yaverbaum, right? Which, like, even we laugh at. I mean, we can all laugh at that name. Like, that is not a reward for good behavior in the pre-life, I can assure you. But anybody I've ever met, anybody I've ever heard of with the name Yaverbaum, I know how they're related to me. Like, I've literally never met a Yaverbaum or even heard of, even on the web. I haven't seen any Yaverbaums that I don't know how they're related to me somehow. And as you can tell from me, like, clearly I have like cousins in my background that married each other. I mean, this is what happens. But okay, I'm just kidding. Okay. Yeah. So what parameter means, what I'm saying. Yeah. So actually, parameter is very different from a condition. I'm saying here, the definition of a. All right, I guess I should write it down. All right, I'm going to write it down. Sorry.
Professor, after it says feature of each system, what does that word say?
Oh, sorry. Yeah, you're right. It says my handwriting. So ingredient is what it's meant to say. Hold on. Sorry. Ingredient. Good question. Sorry. Hold on.
Thank you.
No problem. Cool. So to everybody, and this is worth, I mean, these are good questions and I appreciate getting them. And this is worth stopping. Or I maybe now that I've stopped this long, I might stop even longer. Like what I'm trying to say is these are different types of constants. What I'm really trying to stop and say is, in math, we have variables and we have constants. Now they're both generally letters at this stage of the game for all of us at this stage of the game in physics and math. You notice we're dropping the numbers. Math isn't really about numbers anymore. It's about letters all the time. And same thing with physics, because everything we're doing is in general. It's like what would be true in the universe, not for any one specific arbitrary example, which is really where math and physics start getting intimidating to some people sometimes. If they're not it seems to come out of nowhere. But math doesn't look like math anymore. It looks like all these letters. Because we're doing things in general, but the different letters are different types in math, right? Like some of the letters are variables, meaning they're standing for numbers that are changing all the time, but other letters are constants. They are standing for numbers that are not changing all the time, right? And you have to know the difference. Otherwise the equations don't make any sense. Generally, sidebar, generally the constants are letters from the beginning of the alphabet, like A, B, and C. And generally our variable letters are from the end of the alphabet. But that's not a hard and fast rule. So you got to get used to it. Now I'm saying in physics, and in math, there's two types of variable, dependent and independent, and it really makes a distinction. And you've all been hearing about dependent versus independent since you were in 7th grade. But if you're like me, you fuzzed out that distinction, like from when you were in 8th grade. Like it was a thing that teachers make a big deal of for a while, and then it seems to stop mattering. And maybe you kind of in your mind are like independent variable means input and dependent variable means output or something. And that's right. Like, don't lose that if that's what you're still thinking. That is right. I'm here to say it really makes a difference. If you're going to be a scientist, independent variable kind of ends up meaning like cause. And dependent variable kind of ends up meaning something like effect. I mean, it's not exactly the same thing because we're very careful about cause effect in science, but the independent variable is the variable that drives, and the dependent variable is the one that's being driven. That's an important distinction between variables. Now, similarly, in physics here, we have a distinction between constants. What I want to tell everybody is there's all these constants flying around in our equations. K, M, X naught, they're all constants, but they are of different types. They're all numbers that don't change once the system is doing its thing. So in that sense, they're all constants, but for different reasons. One type of constant is called a parameter. A parameter is a constant material property. I should say these are both types of constants. I guess I didn't actually say that. Sorry. A parameter is a material property of a system. It's something that you can measure each piece that you made your system of, and you can even measure it at the factory. You can, in other words, you can measure it and know the measurement before you do anything with the system. That's what a parameter is. So like our mass spring system, the mass and the stiffness are parameters. They are not going to change no matter what even once the system is doing its thing, once it's going back and forth. They just are what they are. Right. Wait, I'm just looking. Right. So like what Kirsty's saying, awesome. Yeah. 3 kilograms in mass equals 3 kilograms. 3 kilograms is a constant, and the specific kind of constant that I'm saying it is, and I think this is what Kirsty's saying also, is that it's a parameter, because it doesn't even matter where I put the mass at all. It still has that mass of 3 kilograms. It's just a description. Like I could put that description in if I were writing a research paper on this experiment, like it's just one of the ingredients. But configure it. Oh, cool. Okay, great, awesome. And that counts as a full circle thing, blah, blah. Awesome, Kirsty, yes, awesome. That's a million points. And I'm not being sarcastic, I'm just being silly, but true. But configuration is a different kind of constant. X naught, like notice these were all givens. They were all givens in homework 1. Like they're all given constant, but they're different types of givens. X naught is where we decided to bring the mass, like we decided to hold it at 15 centimeters from the equilibrium position before we started. And then we let it go, and then it went wah, back and forth between 15 and negative 15 centimeters, right? That was its initial condition, its configuration. It was part of not the ingredients of the system, but what we did with the system, how we set it up. We had other choices. We could have started this mass at 30 centimeters from the equilibrium, and all of our general math would have still been the same. Oh yeah, I'm going to look at that one second. So all of our general math would have still been the same, but our numerical results would have been different. Some of them, right? Like it would have gone back and forth between 30 and negative 30 if we'd done that, rather than 15 and negative 15, right? So that it still would have been a mass of 0.3, but it would have been like our measurements would have been different if we set it up, if we configured it under a different condition. There still would have been constants, but they'd be a different constant from the other way. Let me just check Catherine's thing and then say, oh wait, oh I did. Are you sure? Okay, cool. Oh yeah. Oh great. Oh actually, that's a great question, and you should totally submit that. And if I answered it, good. So I won't. But yeah, the answer is yes. But that's a very clever way of making sure that you understand what I'm saying. Yes, you're right, Catherine. So now here's all right. As long as we are, if this is getting clear to people, so what I'm really trying to say, first of all, is okay, I might be dragging this out, but this is a huge point. What I'm trying to say, and I appreciate Catherine's question and Kirsty's question, and I think other people's totally on point questions, or maybe one of them was a direct, sorry, but this is the actual essence of harmonic oscillation. Like we're here really probing the mathematics of harmonic oscillation. The mathematics get abstract, but the reason, one of the major benefits of this mathematical journey into harmonic oscillation is that we uncover this feature of what harmonic means. Harmonic ultimately does mean constant. It means there's something very constant and regular about this oscillation. All of you knew that right from the get-go, or at least you hoped that, or you predicted that. Like, I think all of you, and we found that in question 4 or something of homework 1, all of you were pretty comfortable in picturing like, all right, if there's no friction, I guess this thing's gonna go back and forth in the same way forever, back and forth in the same way forever. And if I asked you, is it gonna go in the same rate forever? Like, if it takes 2 seconds to do the first swing, do you figure it'll take 2 seconds to do the second swing? And I think most of you, especially if you were on an exam or something, or if I like cornered you, most of you would say, yeah. Like you might say, well, I don't know where you got 2 seconds from, Yaverbaum. And I would say, I'm just making that up. Like, I don't know if it is 2 seconds. Like, I don't know what it is, but whatever it is, if it's taking 2 seconds to go there and back, or 5 seconds, or even a minute, whatever it is, do you figure it's always like going to be a minute to go back and forth? And I think most of you would have said yes, and you'd be right. It's not true of just any random oscillation. It is true of a nice tidy oscillation where energy is conserved, where Hooke's law is observed. What I'm saying now, though, is it's even stronger than that. It's actually even more interesting than that. If the oscillation is truly harmonic, which is what we're talking about here, if it's truly harmonic, if it truly obeys that differential equation, otherwise known as Hooke's law, if it's truly harmonic, then not only will every swing take, say, 2 minutes? Like if the first, or a minute, say the first full cycle takes a minute, then not only is it true that the second cycle will take a minute and the third cycle will take a minute, but the fabulous, bizarre, surprising thing is that that minute amount of time that you're like, I don't know where you're getting that, Yaverbaum. And I'm like, well, for the moment, I'm making it up. But whatever it is, now I'm saying, well, I don't have to make it up. I can actually find it now. We have the math to find out. We have the math. Once we write down the differential equation, in order to find out how much time that first swing will take, basically all we need to do is look at the square root of the constant in the differential equation. And it's going to give us all the information we need to know about how much time each cycle is going to take, or put it, which is called period, or put another way, how many cycles there will be per unit time, which is called standard frequency. We're going to get all of that from just automatically knowing the angular frequency, knowing how many radians per time that cosine function does. And we're going to know that, here's the kicker. In some ways, I've said this now 5 times, but in some ways, I guarantee I haven't said it at all yet. In some ways, the kicker is that that angular frequency that we can immediately get by just taking the square root of the constant in the differential equation, that angular frequency is fully determined by parameters. It is not at all determined by conditions. So what I'm really saying in English is that as long as I know how massive that mass is, and as long as I know how strong that spring is, I don't care how far back I bring the mass, it's going to vibrate at a certain rate, at a certain angular frequency, a certain standard frequency, a certain period, whatever you want to call it, a certain wiggle rate. That thing is going to undergo a certain wiggle rate, which has nothing to do at all with how far I'm asking it to go. That, I'm going to say again, because that is crazy. I'm going to now say for maybe the 7th time, and I'm thinking I'm going to say it a 7th time because maybe some of you have realized that I've said it 7 times. Maybe some of you are thinking, wait, he said that already. But I'm telling you, even if you've heard me say this already, you got to really let it sink in, because if you think it makes sense what I'm saying, you probably haven't heard it enough, because it actually doesn't make sense. I mean, it does, but it's really weird. I'm literally saying, here's what I'm literally saying. If you to believe, sorry. I'm really trying to analyze what this means, okay? Or I'm really trying to analyze what this means, however you want to say it. And I'm going to just keep writing these things because they're so powerful, at least to me. I'm saying if you kind of understand what that omega is, that it's wiggle rate, and you kind of understand that I'm saying that that omega from here on in is just going to be the square root of whatever the constant is in our differential equation, whether it's a mass on a spring or a pendulum or a temperature system, whatever it is, that wiggle rate does not come from or look at in any way Z naught or X naught or A or whatever you want to call the 15 centimeter thing. Therefore, what I'm really saying is, if I pull our mass spring system from homework 1, if I pull the mass out to 15 centimeters and let it go, and it goes wah, 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 right? And we do our calculation and we find, oh, it looks like that thing is going back. It looks like that thing is going back and forth 13 times a second or something, or 27 radians per second. Or we find, oh, it looks like it's taking one full second for that thing to go there and back. Like we find that out from our calculations. And we find that out for one that is stretched to the 15 centimeter mark. We find out that's going, oh, 1 Mississippi, oh, 2 Mississippi. Oh, 3 Mississippi, right? If we find out, what I'm telling you now is if we start all over again with the same parameters, the same mass, the same spring, but we change the configuration. We start all over again with these ingredients, but we hold the mass out at like 30 centimeters instead of 15, or we hold it out at like 45, like whatever the spring can handle. We hold it out at 1.5 meters if the spring can handle it. And we ask it to go like, wah, 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 right? Which we could do if the spring is like big enough. If we set up the same spring, but set it up way over here, and asked each swing to be like 90 centimeters long instead of 30 centimeters long or whatever, I'm saying it's still going to take a second to go there and back. I'm saying we can't change that fact. Even by changing the distance that we ask this oscillator to go, we won't change the time. The time will be the same no matter what the distance is. If it makes short swings, it's going to make them on average really slowly. If we ask it to make big swings, apparently, according to this math, it's going to make those swings really fast. And it's going to like at a high average velocity and fast enough so that it'll get there and back in exactly the same amount of time that it would have if it had been a really short amplitude. That's what I'm trying to say. That is a surprise. There's no reason to believe it at all. It really, because it's really counterintuitive. I'm saying no matter what spring you set up, it'll adjust its speed perfectly so that the time is always the same for any distance. I would never expect that. Now I would, if I think about it a long time, like I am asking you to do now, and some of this, maybe you want to go home and think about it like this page of notes or whatever, but I'm like, first, again, if you don't hear what I'm saying at all, you want to slow it down and think about it. If you hear me, but you're like, yeah, duh, then I don't think you totally get it, to be honest. Like, if you're just like, duh, no, first ask yourself, wait, he seems to be making a very big deal of this. He seems to be saying that it's not just a duh. So first you might want to ask yourself, why wouldn't anybody expect this? They wouldn't expect it because I would expect that farther trips would have to take more time. Okay, one second. Hold on one second. Hold on one second. Sorry, I just got distracted. But my bad. I'm going to keep going for a second, but and no one interrupted anything. It's my bad. I'm just going to keep going for it. But yeah, okay. I want to make a big. So again, this is. I think I might be. So I'm trying to make a big point here, but it may seem. Again, it's like always. To some people, it may seem like I'm spending much time on something that I've already said 3 times, or that's not helping you with the homework. And by the way, in a minute, I do just want to get back directly to the homework because I think that will help everybody. I think partly I'm trying to explain something here that is, I'm trying to put in perspective kind of why we've done all this calculus. Right at this very moment, I'm actually not. I recognize that right at this very moment, I'm not really trying to do anything directly with the calculus. Right at this very moment, I'm trying to say that if we did all this calculus yesterday and stuff, if we ultimately, basically what I'm really trying to do right now is say that this thing that we found, that I just circled, omega equals k over m, is a big deal. What that statement is saying is that omega stands for wiggle rate. We call it angular frequency, but it really is the rate at which this thing cycles back and forth. We'll see that more concretely when I go back to the homework in a moment. What I'm trying to say to everybody is that it's actually really interesting and surprising that the wiggle rate, the rate at which this thing goes back and forth, is determined only by how heavy the spring is, how stiff the spring is and how heavy the mass is. Ideally, everybody ultimately will follow all the math we did to get to this point, ideally. But even if right now, some of us are like, wait, how are all these pieces fitting together? Like, what's he even talking about? What I'm trying to say right now is we put together a lot of calculus pieces in part to get to the point of realizing that, to get to the point where we can predict the rate at which this thing goes back and forth. The rate at which it goes back and forth, or the simplest way to see it, is called omega. It turns out that omega, we proved, is determined fully by the stiffness and the mass of the spring. We'll go back over that a number of times, but maybe right now this is almost just motivation to know why to care about the calculus and everything, is that what we seem to be finding is that the rate of this mass on the spring doesn't have to do with how we set up the mass on the spring. It only has to do with the mass and the spring themselves. This is the essence of harmonic oscillation. I'm going to say, and it's really an astounding discovery. Just to put in perspective what I'm saying, I'm going to say but it's also this. I might not have spent this much time right now. Frankly, part of the reason I am is because I was so thrilled that a number of people in the class were asking me to slow down and specifically say what I meant by parameter and configuration. It just showed me that people were paying attention, and as long as they were, and as long as people were that much with me to even ask me, I decided to like really dwell on this for a moment. And maybe that's a bad choice. Maybe I'll move on in a second. But I'm going to try but this right now is meant to be, when I'm talking to everybody, is meant to be larger perspective on why this material is kind of interesting, historical, and maybe why the calculus is worth it. I'm not expecting anybody, this doesn't make anybody better at calculus, what I'm saying right now, and it doesn't really help anybody really right now if they're worried about calculus. But I'll say this, but also let me repeat, I sucked at calculus until I didn't. I mean, to put it, like I spent a long time sucking at calculus and wanting to give up on it. But I had certain motivation to continue. And eventually I'm still not better at it than some people, but I'm better at it than some others. I'm good enough at it to be able to understand the things that I want to understand in life. And that's what got me through it. So let me give you a quick example of motivation, or what this is about. So just, in an effort to hang on maybe and keep, no problem. And that is I'll say this quickly. You'll either land or it won't. Galileo, the great Galileo, who is one of my heroes, surprise. He's sitting in the Sistine Chapel. And this story is fairly well documented, by the way. This is not like Newton sitting under the tree and an apple falling on his head, which I don't know if that ever happened or if it ever had the significance that cartoons tend to say that it does. But Galileo, for real, did spend a lot of time in chapel, including the Sistine Chapel, which is like beautiful. And apparently he's there, and he's supposed to be like worshiping, but his mind is wandering. Surprise, surprise. And he's looking at
although he was a very worshipful guy. But he's looking at chandeliers, these enormous long chandeliers that are hanging from the ceiling of the Sistine Chapel, chandeliers that are very much like the pendulums that you looked at in lab 2, right? I mean, they're elaborate, they're complicated, but they're like a big object sitting at the bottom of a long string. And the chandeliers are going back and forth, or a chandelier is going back and forth like this at a seemingly steady rate. And he gets curious and notices, like, wow, because there's wind like through the shaft. I mean, this is not like a New York City, this is in the year, like, let's say Galileo was born, Galileo was born in Galileo dies in 1642. So this is probably like in the year like 1620, like AD, something like that. So it's not an air-conditioned building. And there's like wind blowing through the cracks in the building, and the chandeliers going like this. And Galileo notices and conjectures in his mind. He's like, whoa, that seems pretty steady, the way that thing's going back and forth. I feel like that thing is kind of always taking the same amount of time to go one direction as to the other. And decides to start considering that and start verifying that, and starts thinking, can I verify that each swing takes roughly the same amount of time? And then he notices, though, like, this is reality. This is real world. This is not a physics lab. There's no such thing as physics labs yet. He's the guy that sort of invents the idea of a physics lab. He's just in reality. And of course, in reality, there's friction and there's damping effects and things like that. There's frictional effects on the string itself. There's frictional effects on the candles that are hanging from the string. And so, of course, in reality, the swings start getting shorter and shorter in distance. Okay, now I'm talking to everybody here, just to put perspective on this point. This is not a calculus thing that I'm saying. This is like a English thing that hopefully will put in perspective what I'm saying. But it's real. He notices that each swing of the pendulum gets shorter as time progresses, as the church service progresses. And of course it does. Like this is what happens in reality due to friction. It might have even happened to your pendulum in your lab. We would say the amplitude of the pendulum, the maximum displacement from equilibrium, keeps getting smaller and smaller as the pendulum is oscillating. So first it makes a swing that's like, say, 30 degrees in arc length, or however you want to say it. And then it makes a shorter swing, and then a shorter swing, shorter in distance, right? The pendulum's getting closer and closer to just being tiny, tiny, almost vertical. It started like this, it started like this, and now it's getting to like this, right? Now that's total reality. That itself is beautiful, but it's not surprising to any of you. I mean, that's what pendulums do. They swing back and forth, they oscillate, and in reality, with friction, their swings get shorter and shorter in distance. But Galileo noticed, half consciously and informally, without measuring equipment, he noticed, like, wait a second, even as the amplitude is damping out, even as, he might not have used that word. In fact, he definitely wouldn't have, because he'd be thinking in Italian, but he would think, wait, even as the amplitude is damping out, is getting smaller, the frequency of this pendulum, the period, whatever word you want to use, the angular frequency, he wouldn't have had that word either, but the rate of this pendulum seems to be holding steady, even as the lengths, the space of each swing is getting shorter. The time duration of each swing does not seem to be very much affected. He noticed that. Now that is not the part of the reason someone might be confused right now is that what I'm saying is confusing. Like, what I'm saying is, it took Galileo to notice it. It's a very hard thing to notice, because your brain wouldn't expect that. Your brain wouldn't be looking for it. You'd think the shorter and shorter. In fact, even my language makes it confusing. I'm saying the swings get shorter and shorter in distance. So your brain probably automatically then thinks, oh yeah, shorter and shorter, like quicker and quicker. But what I'm saying is, no, even though they got shorter and shorter in distance, they didn't get less and less time. If this first swing took about a second, it turns out Galileo conjectured, like, I feel like that last swing, even that really short one, I feel like it also took a full second to go all the way there and back. And he tested it. He tested it. He made a measurement. Now, how did he make a measurement? That's an interesting question, because you'd have to make a clock. I mean, you'd have to have a clock to make a measurement like this. They didn't have mechanical clocks that were very reliable back then, because they didn't know how to make systems that kept time very reliably. What he did right there in order to informally test his conjecture was he used his heartbeat. Is that perfect? Heck no. But is it better than nothing? Heck yes. And could he have sat there and actually sung a hip hop song instead and just kept a beat with his hands and used that as a clock? Heck yes. Would that be perfect? Heck no. Would it be a huge advancement nonetheless in precision? Heck yeah, because that's why hip hop works, because it does keep a steady rhythm, which is like all that time is a steady rhythm. So Galileo used his body. He used his heartbeat to at least begin to verify his informal conjecture. And sure enough, he was like, heck, oh my God, whatever he said in Italian. He was like, oh my God, even as those swings are shorter in distance, they don't seem to be taking any less or more time. It seems like if to go all the way there and back the first time takes a full heartbeat, let's say like one of my pulses, it seems like the next one also gets back to its original position in another heartbeat, even though he could see with his eyes that the amplitudes were lesser, the periods were not lesser, which could, if that's true, could only mean, oh, and sorry, and then he went back to the lab later on. And what he did with that, he trusted it enough to start making clocks out of pendulums, because he believed from his body that that pendulum was actually serving as a clock, like something that could keep steady time even when the space around it was being affected. So he became a master. I mean, he's not the only one, but he started making reliable timekeeping devices out of pendulums and other things, and then using them to further verify his conjectures. Everything builds on itself. Nothing, there's no absolute, like, he can't ever just turn to Moses or Jesus or Muhammad and say, like, so do I have my science right? Like, they might know, but they're not going to tell you, right? And like, I don't know if they know or not. The way science does is it builds from truth to new truths, etc. But Galileo was right. It turns out all this math is like that much more rigorous, and all of our equipment these days is that much more precise. What I'm trying to say is Galileo first realized exactly what I'm trying to say here, which is that if something is a true harmonic oscillator, it will vibrate, it'll oscillate with a rate in time that does not depend on distance. That's what I'm trying to say. A rate in time that does not depend on how you set up the oscillator. Even swings of a pendulum that are shorter in distance are swings that have less and less potential energy at each end, therefore less and less average kinetic energy, therefore less and less average velocity or speed, and just enough less and less, it works out perfectly, that shorter distances will be smaller speeds and therefore accordingly the exact same amount of time as longer distances. That's what this means. Okay, I'm going to go back now. I have to go back to the homework, obviously. I don't know if that helped anybody or if it dragged or if it like put everybody in the dust, but I'm ultimately saying that a harmonic oscillator is an oscillator that obeys the differential equation we have. It could be a mass on a spring, could be a pendulum on a string, could be a temperature system, could be an electric field, doesn't matter. As long as the differential, and here's the calculus part again, as long as that differential equation applies, the system will oscillate with an angular frequency that is the square root of the constant in the differential equation, and that constant does not get affected by amplitude, does not get affected by conditions or configurations. It only gets affected by parameters. So that's how powerfully constant harmonic oscillations are. In short, a harmonic oscillator is a clock. A harmonic oscillator is a clock. It's something that keeps time steadily, regardless of other factors. Any way we've ever made a clock in the history since the 17th century, any way we've ever made a clock has been out of some kind of harmonic oscillator, whether it's a pendulum or a spring or an electric circuit. Clocks are harmonic oscillators. They are timekeepers. All right, that's probably too much for everybody at this point. I'm going to go straight to the homework. I'm just going to keep pressing. I'm going to go to homework. I almost, based on all that, we literally could do homework 3 right now. Any of you who's tried it knows that. Any of you who's not tried it, you could literally do homework 3 now, actually, based on everything I just said. But I don't want to confuse people or freak people out. So I'm going to go to homework 2 now, and this will give more practice with the calculus. We'll go back to the calculus and hopefully fill in some gaps for anybody and everybody. Anybody who's still lost in the calculus, I understand. And I do want to talk to you privately. I want to know anybody who is feeling intimidated by the calculus. The only thing I ask is don't give up on yourself and don't think I've given up on you. Like, keep tuning, even hearing things that don't make sense do help. Like, one last final way to, or even if you're not lost in the calculus, but you can't stand the last 15 minutes, I was just like talking about history. The deal of school, it took me a long time to realize this too. One of the reasons to take notes or even to go to class is not to learn the thing then. You don't actually I'm trying to make sense out of this stuff right now, but that doesn't mean sense is not going to automatically happen in your brain right now just because I'm trying to. What you're there to do in part, all of you, is take notes and listen so that you find out what it is. You're there to find out what it is that I'm asking you to understand. And then what we do is we go home with homework and with each other to continue to try to understand. I don't expect that you get something the minute I say it, but I need you to know what I'm saying so you know what to work on understanding, or both of us together. I'm going to look into it. So even if the calculus is still, and we're going to get more practice with the calculus stuff, especially in homework 2, which is where I'm going now. I'm just always trying to do too many things at once. But again, as long as there's no shame in any direction, as long as you guys are not ashamed of not understanding what I'm talking about yet, but still listening, and as long as I'm not ashamed of you not understanding that, let's just keep listening to each other, and it will fall more and more into place. It will. Let me just, right. No. All right, good. More and more people in the direct chat are admitting to me. I am getting direct chat things about people's struggles with calculus. I totally hear you. Again, and it's good information. And I don't mean to like stop on a dime every time I get a direct chat. Sometimes I do, sometimes I don't. But if I do, that's my decision. Like, if I stop on a dime for a direct chat, that's me. That's not you. You're allowed to send a direct chat at any time. And if I'm spazzy, I'm spazzy. But that's why it's direct chat. For real, everybody. Like, this is ideally what this is 29 simultaneous but independent tutoring sessions, if you know what I'm saying. Like, I'm not really here for the group. I'm here for 29 individuals. It's just, I can't obviously really do that all the time. So I'm always making sacrifices, but but it's not a crime to write things down that I say about calculus even before you get them, and note, like, this is something you have to ask me about later or whatever. And it's also not a crime when I get to the exact point in calculus that someone doesn't know to tell me right then, yeah, this is where I have no idea what you're talking about. That's good too. But just don't totally tune out just because you think I'm on a topic that, okay, last way of putting that, I'm never saying anything here because I assume you already know it. That I think would be a waste of time. I'm saying things here, hopefully, to get you to know them, all of you. So I'm always afraid of boring people too, but I'm not assuming anybody knows anything. I'm assuming you've seen things and that's it. But all right, let's go to the homework 2. Homework 2. It might be this. So homework 2 now is like from the abstract to the concrete. It might be a big, yeah, this might be a big transition, but it might be the transition that everybody needed for a long time. Hold on, now I'm just going to pull mine up. Pardon me for a second. And again, if you've done this already, then this will be confirming to you. If you haven't done it, this will be helpful, hopefully. Sorry, I'm just pulling it up. Okay. Okay. So I'm going to start playing through homework 2 now. Also, please note, everything is meant to fit together in this class. Ultimately, every ingredient is meant to be an ingredient that fits together, but they are all ingredients. So sometimes it's best to just look at every ingredient in and of it. Like, there is a context for this. This does fit with other things we're saying, but especially if you find it intimidating or whatever, don't overthink. Don't try to over ask yourself, why is Yaverbab asking this? Or why is Wu asking this? just see if you can do it on its own terms, because it might be that doing it is meant to help you with other things. So what I'm saying is on this first one, back to the screen. Okay, yeah, like in a way, just out of nowhere, I'm walking through the forest and someone's just giving me this review calculus problem. Here's a function called x equals a cosine omega t. There are some assumptions being made here. Maybe I should have made clear in the sheet, like we're assuming constant, and we're assuming constant. Now, in the physics class, often you don't see an a, you see an x naught. So suddenly we have an a here. It's okay. I'm trying to get you used to the fact that, you know, what's important is that it's a constant. It's not the variable. The variables are x. So it might be a different name for the same constant as one, you know, or it might just be a different constant. It's okay. But this is independent variable. And this is dependent variable. Maybe I should use it. Okay, so the first question that's being asked is if that's the function, and if this were a math class, that might say, okay, I'll say this. If this were an old math class, it might be written more like this. Or something, right? I mean, I don't know if that helps at all, but we're using X here the way they use Y in a math class. We're using T the way they use X in math class, and we're just using the other letters the way they use the other letters. So I don't know if that makes it look any clearer, but everything I'm about to say about this is just as though it were a math class and you had something like that. Okay, so what we want to know is what is the derivative of X with respect to T, which is like asking what's dy dx. That whole notation. I mean, and I do encourage you getting used to that notation. There's other ways to write derivative. We're asking for the derivative. I'm sorry. We're asking for the derivative. And there's other ways to write derivative. Oh, and by the way, all of you who are not comfortable with calculus, so this would be the moment to tune in, right? Please don't now think, oh, now he's doing calculus, so forget it. This is not the part for me. No, this is the part for you if I'm doing calculus, because I'm going to try to break it down as best as I can for this context. And I will take questions, and especially honest ones. It's actually the people that totally feel completely solid with this that might want to go get a cup of coffee right now or something and just keep the thing flowing, keep those to see back where I am and stuff. But I am going to try to, I mean, I can't explain it all from scratch right now, but if you had any calculus in your background, what I'm saying is, first of all, we're asking for the derivative here. We're asking for, so this is kind of like asking for f prime, if you're more used to that. I don't use that notation. The prime thing is a problem. I mean, it's not a problem. It's just, I don't think it's as good for a physics context because the using primes doesn't tell you what the two variables are. So I say dx dt means the derivative of x with respect to t. It means specifically that t is the independent variable and x is the dependent variable. So I'm saying let's take the derivative of the right side of that expression up there. Take the derivative of it, treating t as the variable, so treating t as though it's like x, and treating every other letter as though it's just a number. So I could even say, here, let's go to the next page. And I can go back at any time. In fact, okay, for this one, I'm going to try. Okay, this, let's pretend for a minute that this is what we have. And again, for people who are really feel solid with this or already handed in the homework and already got it back, sure, get a cup of coffee right now. And I'm not saying that insultingly to anybody, but I'm not, for people who are a little bit wobbly with the calculus, hopefully this will help a little bit. It won't solve all of our problems, but it might help us for right now, at least for what we need. If you had something like this in math, in a math class, if you had y equals 5 cosine of 2x, okay, here's how you would analyze it. All right. So the first thing I'm saying as a refresher in calculus, again, with apologies to anybody who already feel like they're in command of this, I'm just reminding you, like we are being asked to take a derivative here. And I will try to go back and unpack either in public or in private with anybody really what is meant by a derivative and why it's meaningful and stuff like that. But that's a little too much to do right now. Suffice to say right now, a derivative is an instantaneous rate of change. A derivative is a rate of change. It's like how fast, how quickly the function is rising or the relationship is changing. And something that I guess is kind of a cold memorizer right now, but you might be familiar from math is if you have the function sine of x, the rate at which it's changing is literally cosine of x. That is a funny result. Okay, it can be proven, it can be explained. I will hopefully explain it better soon, but it is a thing to know from math that if the function, if you have y equals sine of x, then its slope at, maybe I will try to say this. I don't know. Hold on. Okay, one way to think about derivatives, once you're thinking of a function as a graph, then it's useful or helpful to think of a derivative as a slope. Like it's like a rate, a steepness, how quickly the graph is changing. So a graph that just looks like this, a horizontal line, a constant function is not changing at all. It has no slope. Its derivative is 0. Like derivative is slope, derivative is rate of change. It's how quickly one variable is varying. So the steeper a graph is, the steeper, a higher slope it has, the higher a derivative it has. Okay, if you look at, but remember, derivatives are things that we do to functions. We said that yesterday. So a derivative isn't always, a derivative becomes a number when you're just looking at one place on a graph or one function. But in general, just like a function is a rule for something that's happening, a derivative is a rule for what the slope is doing. So what I'm saying is if you look at this graph right here, if you turn the page, if you look at that graph, that's like a sine graph, right? If we ask, I mean, that is a sine graph. Okay, that's the sine graph, y equals sine of x. And it starts at the origin, it goes up and then it cross. Okay, so that's sine of x. If you look at that graph and ask yourself at every point, what's the slope doing? If you think about it, right at the beginning, the slope is really high. like right at the beginning, at the origin, like the value of sine is nothing. Right at 0, the value of sine is 0. But the graph is like shooting up from the origin. I kind of wish I hadn't drawn it on its side, but I did because I want to keep this all on one page. The graph is shooting up from the origin at a high rate. So if we were to, so even though the value of sine, the value of the function right there at the origin is 0, the value of the slope is pretty high. The thing is rising up. Then when we get all the way to a peak point, where we get to that high point where the sine is 1, right? Now the slope is nothing. Like right at that top, especially the slope of a tangent line, if you want to think of it that way, right at the top, the graph is neither going up nor is it coming down. It doesn't have a positive slope and it doesn't have a negative slope. It's just right at the top. It's at a peak. So when the sine reaches its highest value, the slope of it reaches a value of 0. Now the graph starts climbing down. The values get lower and lower, but the slopes are getting higher and higher. Do you see what I mean, just roughly what I'm trying to say is if you look at the sine graph, it goes back and forth and back and forth and back and forth. Its slopes also go back and forth and back and forth, but like a bit out of phase with the function itself. The slopes go up and down, but they don't start. But they start with like a head start. When the graph is 0, the slope is very high. And when the graph is very high, the slope is 0. So I'm saying if we wanted to make a graph of what the slopes were doing of that, actually that graph would be the cosine graph. Cosine starts at 1 and then falls down. And when we get to an angle of 90 degrees where the sine is 1, the cosine is 0. I'm saying a lot in a way, and I don't mean for you to write all this down or have your head explode. I'm just trying to argue that derivatives are slopes. And it's actually, and if you think of derivatives as slopes, then it's actually not shocking or weird or out of left field to say, oh yeah, if I picture a sine graph, what its slopes are doing is kind of the same thing as it, only shifted over, like with a head start. And that's what the cosine graph is. The slopes of the sine graph follow the cosine graph. And that's what we mean when we say, and we do memorize from calculus class, whenever you see y equals sine of x, dy dx, the derivative is cosine of x. We're saying the slopes of the sine graph follow the cosine graph. Similarly, we can make the same argument, only just going backwards. If we looked at a cosine graph, we would find a very similar thing, only flipped upside down. Like whenever the cosine graph is going up, the slopes of it are going in the opposite direction. You can think about that yourself. So there's a negative sign comes into play. Don't get bogged down in that. Most people just memorize it at this point. But I'm saying now to anybody who's left listening, actually, I should really look at the video. Whoever's left listening, and hopefully this is helpful to some of you. I'm saying what we take away from math class is that the derivative of sine is always cosine. Oh, cool. Oh, thank you so much. Oh my God, that's really helpful because I do feel like oh, that is so nice. Okay, someone just made my day. Okay, that's major point. No, but seriously, I mean, like I'm glad if this is doing anything for anybody. And I want to also put perspective again. Like I do feel all of this stuff can be broken down if we had enough time. I wish we had more than 5 weeks. But I also want to be honest. Like I know some things we eventually just put in the box and we memorize them. What do you need to know for this class or whatever? What am I pulling from calculus class that I'm right now quickly trying to justify? Yes, I want everybody in this class to feel just comfortable enough with derivatives to think of them as slopes, as rate of change, and to know that, yes, from here on in, it will come up a lot. The derivative of sine is cosine. The derivative of cosine is negative sine. Like either sort of, appreciate why, or if you memorize it, that's cool too. That's from math, and it will never be wrong. And I will never ask you to justify that. That is a truism. Now we're going to use it here. Okay. And again, for anybody who's still hanging on, I'm talking a lot right now. I won't talk this much about every piece of math because we're not trying to redo all of math. These are just the pieces that come up a lot in our class. So don't worry, like we're not going to have to do tangent and all of that. Like we're not really going to use tangents very much in this class. We're just going to use cosine a lot. So, those of you who are still paying attention, you are making a good investment. Okay, so from now on, derivative of sine is cosine, derivative of cosine is negative sine. And derivative of a constant, how should I put this? Well, derivative is slope, right? Derivative is slope. So whenever you look at any function like y equals mx plus b, the slope of that, that's a straight line, y equals mx plus b. The slope of it is m, whatever m is. So if you look at a function like y equals mx plus b, its slope is m, therefore its derivative is m. I'm saying that fast, you might remember that, or you could think of that as a power rule or whatever, but that's my way of justifying that whenever we have, yeah, totally. Wait, is that Shaki? We will be using a lot of derivatives, yeah. But honestly, so I don't know if that's good or bad news. We also will be using a lot of integrals, to be truthful. But right now we're heavy on the derivatives. But the good, so yes, whether that's good news or bad news, like Shankia, and I'm glad you put that in the public chat, we will be using a lot of derivatives. But I can also tell you the reason I'm spending this much time on these derivatives is it's basically just going to be these. It's not a whole bunch of different derivatives that we have to do all the time. It's kind of these over and over. So there's some level at which you could just sort of like, once you get used to what we're doing here, you'll be fine. But yes, we will be using these derivatives a lot. So I think what what I'm trying to say now is, oh, sorry. Okay, so now I'm saying, so I've just tried to justify what to do with the cosine part. Okay, cool. Thank you, Shakia. Okay. Now I'm saying, what do we do with the 5 part? Like, so I'm trying to analyze this y equals 5 cosine 2x. And I'm telling everybody, by the way, this is the thing. If you can, by the end, if you understand what I say about the derivative of 5 cosine 2x, then that's just a numerical example of exactly what we're doing in the homework and in the class. Like, this is just, it looks clearer, hopefully, what I'm doing right now. But this is all an analysis. Like, if you can get this, it's not going to be any harder than this, I guess is what I'm trying to say. It's just that we're substituting letters for numbers, ultimately. But so what I'm saying so far.
Can you go back, Professor?
Oh, sorry. Yeah. Sorry. To that.
Yeah.
Okay. So this page, what I'm trying to say now is what we're going to do with the 5. Like the last page, I just tried to justify what we do with the cosine or sine part. And I'm sort of saying that cosine is going to turn into a negative sign because we're trying to take derivatives. Now, what do we do with the 5? What I'm ultimately trying to say is the 5 is just going to stay there. It's going to sit there because 5, to have that coefficient, to have any graph or any function sort of multiplied by 5 like that at the beginning, basically means that you're taking the whole function, like as if the whole function were x, you're multiplying it by some m. And you all know from your original math classes, like y equals mx plus b, that multiplier m, it just tells you how steeply, how quickly that straight line rises. That m is the slope, which is the derivative of y equals mx plus b. In other words, if there's a 5 sitting here in our expression, we're going to keep that 5 sitting there because it's saying that the graph is rising that quickly. It's rising at a rate of 5. So our answer, so in other words, any coefficients like that in an expression you keep in the derivative because they're part of the slope. So the only thing left I have to analyze to get an answer here, the thing I have to do last is what do I do with that 2 that's sitting inside the cosine? And this is what I was saying yesterday is called the chain rule. Okay. I'm going to turn the page in a second. And I know, and again, I think this is really good. I keep apologizing just because that's my nature. But the truth is, I think this is what class should be. If even 2 people are getting anything out of this that wasn't clear to them, and it sounds like at least 1 person in the direct chat is, if anybody here is having anything click that didn't click before, then this is totally worth it for me, really. And I don't care if we never get to something. Like, this is what it's supposed to be about. I keep apologizing to people that feel like, if there's anybody who feels like they're not getting their money's worth because this is something they already know, I apologize to them, but their moment will come. Their money will be, like, I feel like there is any point in math and physics we could stop and break it down to this level and bring it all the way back to basics. And that's actually the thrill and the fun of it for me, any point. So it's anybody who has the guts to stop me and say, I need more help with this, I will do this. And again, those of you who want to go get a cup of coffee, there's no insult to me, just as long as you like don't get fed up with the class and run away and say, I can't believe he's never going to get to blah, blah, blah. Cause like I will, but okay. Oh, good. Oh, thank you. That's 2 people. Okay. So no, I do that. Oh, good. Thank you. And I'm not like fishing for, well, I guess I sort of am, but no, cool. I now totally feel like this is justified. So great. And again, and those of you who are being patient about it, major kudos. Oh, I'll put in a portal for that too. I'll think of a portal for that, of like rolling with stuff that I think I already understand. There's something, but okay. And just as long as you all understand that I do understand this stuff now, and I love talking about it, but I did not understand it until I did, if you know what I mean. Okay. And I did not when I was supposed to. I did ultimately because I put myself into publicly embarrassing situations year after year where it's like horrifying if I don't understand it. That's how, like, I never got it when I was supposed to. So there's always still time. Most of you are ahead of me, I assure you, in this trajectory. But okay, so where we are now in this is like we're almost there. To remind you again, we're trying, and tell me if I have to go back, but we're trying to analyze this thing as an example of what we're really trying to do in the physics homework, but we're trying to analyze this. Okay, what I'm saying so far, thus far, what I'm really trying to say is, just to be as clear as possible, is I think that I've established what to do with cosine and what to do with like the 5, or what we'll ultimately call the coefficient or the amplitude. If we had y equals 5 cosine x, and again, I don't want to confuse, that's not the example in the homework, right? I'm breaking it down. But if we had y equals 5 cosine x, I would say that dy dx equals -5 sine x. The negative sign coming from the fact that the derivative of cosine is negative sine, and the 5 is just sitting there, staying for the ride because it's contributing to the slope. Like, and if you understand that much so far, that you could totally memorize. You can. Yeah, like if you even see what I'm saying, that will never let you down in this class. Like, you can always do that. And now what I'm saying, so now and if you get what I'm saying, you'll see it doesn't matter if it's a 5 or a 7 or the letter A or the letter X naught. Whatever it is, as long as it's a constant, it'll just sit there for the ride. And the negative sign will come in as long as we're going from cosine to sine, but it won't come in if we're going from sine to cosine. That's just a funny peculiarity that, like, I guess you can memorize. Like, I didn't really justify that, but it's just, if you really look at the cosine graph and the sine graph, you'll see that it's true. So now the only thing left I have to do is watch the time and deal with this 2 that's in the argument. And then if I deal with the 2, then we'll be as complicated as this gets. I'm just going to look at the chat first. I'm actually, okay. Yeah. Oh, cool. Yes. Okay, great. Oh, cool. Oh, I'm loving everything in the direct chat. Thank you for the nice comments in the direct chat. And thank you for those of you who are keep quiet here. But Juanita's, yes. Totally, yes. Any good. First of all, thank you for saying you understand. But second of all, yes, any constant, here's the key thing. Any constant, as long as it's before, as long as it's at the beginning out front, as long as it's multiplying the whole function, then it'll just stay. Yes. As long as it's out there in front, it'll just stay. Yes. The only issue is now, what about that constant that's inside the parentheses? That's the slightly more confusing thing, because so yes, I mean, the answer to Juanita's question is yes, as long as the constant is out front, multiplying the entire expression. But this 2 business, to go back a page, this 2 is inside the cosine. That's actually trickier. That's actually a different issue now, because now what we're actually saying is, rather than, in addition to taking cosine and like multiplying it by 5, we're actually not taking the cosine of x. We're not just doing a thing to x. We're not plugging x into a cosine box and popping something out. We're actually, before we even put the x in the cosine box, we're first evidently multiplying it by 2. In other words, we're doing a function, we're doing something to x before we even do the cosine function. And even if I put a plus sign in the parentheses, like even if I wrote x plus 3.5 or something, I would still be making this argument that, what we have here is a function, what we have here is a function of a function. It's a function inside a function. We're doing a rule before we even do the rule of cosine. Whenever we have that situation, a function of a function, that's when we apply something from calculus called a chain rule. It is a different rule. It's like we've dealt with the cosine thing, that's one rule. But then there's this thing called the chain rule. Sorry, have I lost my pages? Oh yeah, for this we use the chain rule. Yeah. And the chain rule says, and we did, so I might say this a little faster because we did say this yesterday in class, but it might not have meant anything then. The chain rule says, oh yeah. Yeah. Oh, cool. Thank you. Oh, yeah. A function in a function. Right. Like f. Yeah, like f of g. Exactly what. So I'm agreeing with what Shankia put in. Juanita, would you multiply the 5 then? Yes, ultimately, that's what's going to. Yes. Oh, you just saved me. First of all, you just gave me like my birthday present. Yeah, totally. You get. I mean, I'm talking to Shankia and Juanita in particular and everybody. But yes, we're going to ultimately multiply that 5 by the 2. Yes, we are. We're going to keep the 2 in there, but we're not going to get rid of it, but we are definitely going to multiply the whole thing by the 2, totally as we did yesterday because of the chain rule. That is awesome. I feel like someone's learning something. That's great. And I'm just going to quickly write it again right here, just for anybody who is tuning in. But yes, the answer is yes. You see, I'm so excited. Okay. But I'm excited because yeah. Okay. So if like y equals f of x and like z equals g of y. So yes, this is that thing of yesterday that basically says if you have I'm writing it slightly different from what Shankia wrote, but it totally is exactly what Shankia is saying. I think I wrote it accidentally backwards of what she said, but yes. A function within a function of a function. Whenever you have that situation, then what calculus says is take the derivative of the outer, which we've done with our business of sine and all that, and then multiply by the derivative of the inner. And the derivative of the inner is indeed that 2. So it's exactly as you're saying. So here, right. So we write out the whole thing, and then we do write out the whole thing, like the 2 does still stay there, like we do the outer function, sort of ignoring all the inner details, and then we multiply that whole thing by the derivative of the inner function. And the derivative of that inner function is indeed 2, because it's like y equals mx plus b. It's like the 2 is the m, it's the slope. So again, I'm agreeing, it's exactly what Juanita said. So we multiply the whole thing by 2, and we're just about finally done. And actually, I also feel like this was worth it, and we are going to be able to relate this back to the homework, which is great. Then like we'd be done. Like if this were a math class, I mean, technically, I guess that's the right answer now. But even a math professor, I think, and definitely a physics person, just stylistically or like aesthetically would then, since the whole thing was already multiplied by -5 and now we're multiplying the whole thing by 2, they would collect those two things together and neaten it up a little bit. And they would say that the answer, they would say, they would say that the answer to this whole thing, they would collect all the constants to the beginning. So they would say this. And this would be the answer to that exercise if it were so. And that exercise was just like it was, well again, was like looked more like a math class, like y equals 5 cosine 2x. That's what we just solved. Now, the good news, and I really do appreciate all the feedback. I do feel like a number of people in the room get this now, and maybe even people that didn't get it before. So that's great. And if you feel okay with this now, the great news is you totally didn't waste your time, believe me. And you totally didn't like set yourself up for badness, because if you get this now, I am actually telling you that the thing that we've been doing something in class for 3 days, and we're going to do something right now in the homework too, go over that I'm sure looked like gobbledygook, like it would make my brain glaze over. It looks impenetrable, but actually all we've been doing over and over again basically is this. You're going to see like it's not any worse than this. If you get this, a lot is going to open up, I think, for a lot of you. It's not like this is one, and this is the other thing. I know this is true in other classes. It can feel like, okay, great. Now he's just explained like one of like 17 different examples, and now I'm gonna have to spend that much time on all 16 others. No, this is actually like at the heart of the 17 things that we didn't really do 17 things. We kind of did one thing over and over, and it was this. So you're going to see now, I think. Oh, wait. Oh, cool. Awesome. Oh, I'm so glad to hear from you. That's great. No, that's really helpful to me. And even if you're good, then, so now you'll, okay. And maybe people, and now you'll also see like why the homework philosophy is the homework philosophy. Just keep trying. Even when you know, the more you can identify exactly what you don't know, that will quickly convert into things that you do know. But okay, I'm going to so now I'm going to go back to the homework. If this makes sense, then where we were, and to the rest of you, I really appreciate your patience. Oh, cool. Wow, there's a lot of people. You know, it really does. Oh, yeah. Oh, now you're ahead of me too. This is great. Now, first of all, thank you again for the good vibes in the direct chat. It's actually great. You know, that's the other thing. Each one of you saying that. So I know that I've only probably pissed off or alienated like 40% of the class instead of set. No, this is great. But also what one person said in the direct chat is now ahead of me. It's great. One person, I'm not going to say a name because it's direct chat, but one person wrote something about, oh, so you can switch from the dy dx to dx dt. Yes. So here's now really the point. If you followed all of that, what I just did, right, in math class, they tend to use y and x. We, both math and physics people, can use whatever they want. But in physics, our variables are tending to be things that come from measurements that we made in the lab or that we care about in space and time. So yes, the important, right, wherever you saw y and x in math, I'm now going to tend to switch to other things in physics. But the important thing is just knowing that they're variables and which one is dependent, which one's independent. Whichever one is on bottom of derivative is the independent. So yeah, totally. That's right. I'm going to now switch it to dx dt, but we do exactly the same reasoning. Wherever you used to see an x, we'll do that same stuff to t, etc. So yeah, so back to, oh, and furthermore, wherever you see just like capital letter or any kind of letters that aren't from the end of the alphabet, that aren't like T and X or Y and X, then they are constants, and you treat them the exact same way that we just treated those raw numbers in a math class. So I'm going to do this one now for everybody. I think everybody gets it, but so if we have x equals a cosine omega t. Looks totally intimidating for sure. But really it's just like saying 5 cosine 2 x. Like, I think you get that. So I'm going to say, maybe I'll get, well, I almost, yeah, I'm just going to do it, but I'm going to say then therefore dx dt equals, okay, I'm going to do it just in the interest of time. I almost want to turn it to you people, but well, I'll just pause for a second. If you want to put anything in the direct chat here, go for it, but don't put anything in the public chat for a minute because I don't want to mess with anybody's thinking. So like, I'll give you a minute just to think and then I'll just do it. So you'll know in your private Idaho whether you're getting it or not. So you could put in the private chat, but don't put it in the public chat for a second, please. And what's going on? Awesome. Yes. Okay, I'm going to just respond to it. Okay, I feel from the little bit I just got in direct chat, I totally feel like people are getting it. I feel like I could retire now, except I totally can't. But no, this is awesome. If you're feeling, if any of you is feeling 1/10 as whatever as I am right now, then we're all really good. But it's awesome. All right. Okay. Wait, sorry. And I didn't expect this today, but that's all the more. Okay, so I'm going to say, wait, I keep losing the, oh. Okay. Great. Okay. You're all rocking my world. I'm moving away from chat for now because I can get too bogged down in it. But yes, those of you who sent me answers in the thing, you definitely get it now. So I'm saying that this is the answer. And so I'm saying this is the answer. And what time is it? Okay, we still got 10 minutes. And if you have the omega all the way at the end, that's correct too. I'm saying it's more sort of traditional physics style and will make our life a little bit easier if we start like shoving that omega to the beginning, multiplying out next to the a. But it's correct either way. And you could put parentheses like this, and you could put, that's a style thing too. But now this might be clearer than yesterday. So that's the first exercise. Then the and that's just that is just a random like function that we just took a derivative of. But of course, it happens that I picked a function that we totally care about in this class, right? Like that a could have been x naught. It would mean the same thing. In fact, often that we use the a. Often people will use it a because it often stands for amplitude. But it means the same thing as x naught, which is the initial position that something is. Now that's pure math. It didn't tell us about any mass on any spring, but the point is that statement could be describing where a mass is at any given moment on some spring. So now we're being asked to take the derivative, the second derivative, and oh, okay. Hold on, sorry. Okay. Okay, sorry. Again, I'm getting caught with it. Oh, there's 5 minutes left. All right. Here we're being asked to take the second derivative. I got some answers in the chat and some questions, so I was just replying to those. One thing that I said this yesterday, but it might be more clear to people now. When we're asking for the second derivative, we're literally asking ourselves to do the exact same thing to the first derivative that we just did to the function. Like it's no new rules. It's the same rules totally. So if we want, and so if you put in the chat, and I hopefully I responded, and I think anybody who did put this in the chat got it right, which is awesome. If we're doing the second derivative, we do the same thing again. First, we look at the outer function. Like first, we just we hold on to that negative and that a because they are constants that are before the whole thing. So they're like the 5 that we were talking about 7 minutes ago. Like they just stay there for the ride. Originally, it was a positive 5 and it just stood there for the ride. Now, then it was an a and it just stood there for the ride. Now it's a negative a. It's standing there for the ride, at least for the moment. And omega, sorry. There's also an omega there sitting there for the ride. Then we look and we see, sine of blah, 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 blah. So the derivative of sine is cosine. So we write cosine. Now, it's again, just an oddity of math that the derivative of cosine was negative sine. So it produced a negative. But the derivative of sine happens to just be cosine. So we're not producing another negative here. That is an oddity of this. It's just a fact. So we do cosine of omega t, but then now we're doing chain rule because we're doing function of a function. And the inner function is omega times t. So the derivative of that is omega. So we have to multiply our whole thing by omega, just like we did before. So we are applying the exact same rule. It's just we're applying it to a slightly different case. So we have this whole thing multiplied by omega. So multiplication is commutative. So I clean it up. You bring the omega to the left, and omega times omega is omega squared. And I'm left with this getting illegible. I'll try to clean up that in a second. And this is the answer. You don't need those parentheses. I'm just sort of putting those to make it clear. This is not clear. But then notice the negative sign does stay this time. Nothing gets rid of it because we don't get a second negative time. We don't get a second negative sign. Hopefully you caught the amplitude thing. Okay, and I'm yes, awesome. Okay, wait. So we have 2 minutes left, so I have to. So let me just finish this. But yes, to Catherine's question, yes. So what this means then, and this is the sort of, even if we've only done this one problem, this is the essence of a lot of the problems from here are repetition and practice in a way. They're all about this issue right here, that what we just got, and this is the last thing, I know we have 1 minute left. And again, for anybody who was coming in and out, the midterm we will post Wednesday night. Oh, sorry, and I guess I didn't resolve this. We'll talk about the midterm like Monday, Tuesday, and Wednesday. You'll have practice and stuff like that. You'll know what it is by the time it's posted, but it'll be posted Wednesday night. Actually, it might even be, you know what? It'll probably, okay, it's going to be posted Thursday night, but you'll have the whole weekend to do it. Okay, so it'll be posted Thursday night and it'll be due by the moment you come into class Monday, probably. I mean, you'll definitely have the whole weekend to do it. I'll get to you exact details like next week on Monday, but it won't be posted until we're going to have 3 more classes to talk about and to do material. And then I will post it Wednesday night or Thursday night, probably actually Thursday night, because I'll probably need time to write it. And then you'll have the whole weekend to do it. It's take home, open everything, not limited time. Again, we'll talk about that more when we get to it, but so it'll be posted after all of our classes next week. But on this, I just want to quickly finish. We have 1 minute. The summary of this problem here in the homework, the answer to Catherine's question is most certainly yes. And that's super important and super awesome that she got that. What we're saying is we just found if X was a cosine omega t and dx, I'm just rewriting this really quickly. Right. This is the last thing I'm going to write. I know we're just about, and if you have to run right now, run, but I'm just about done. what this means, and this is the key. Oh, yes, and thank you very much. See you. I'm just wrapping up right here, and I'll stay for a couple minutes. But this is Catherine's point, and this is the point of the question, is that if we took that second derivative and then we made that observation, that substitution, that, oh my God, that whole a cosine omega t came back to us. Like we took a derivative and it went away, we had a sine, but then we took a second derivative, we got our cosine back, and we got it multiplied by a constant and with a negative sign. So, oh my God, yes, if we pick a cosine omega t as an example of an x function, it does satisfy the original differential equation. It is the type of function which, when you differentiate it twice, you get back itself times a constant times a negative. The constant in this case being called omega squared. So that is a solution to the differential equation. That's just like a way of proving the same thing we're trying to say in the other lectures or in lab. It's just another way of looking at it. But okay, I totally appreciate what everybody has worked hard in different ways today, even people that might have been restless. So I really appreciate it. We will just keep trucking on with this. Obviously, you still have plenty of time to hand in homework 3. We're going to keep going over this homework 2 from this point on Monday, blah, blah, blah. Oh, I got to post. And in a minute, I'll post the like game turn 5 and stuff. But thank you guys very much. I'm going to hold on. Actually, thank you guys very much. Goodbye. Yes, peace.
Thank you.
Thank you. Thank you. I'm going to pause.
Thank you so much, Professor.
Oh, no, thank you. Thank you very much. Seriously. I'm going to pause for a second and post those things before I forget, but I'm not going anywhere. So if you have any questions or want to make an appointment or anything, I'm here.